All right, so we'll be doing section 3.2 next, and really the goal today is to introduce logarithms in this video. By the end of these videos, I want you to be able to use the definition of logarithm to solve one-step logarithmic equations. But along the way, we're actually going to be defining a lot of other pieces as well. So that's really the main goal, but just keep in mind there's going to be a lot of other stuff being defined in this video. So the first thing we have to do is actually define what is a logarithm. Now you've probably seen this before in Algebra 2, but I'm going to go ahead and redefine it just to kind of jog your memory on this. It all stems from, so we'll start with an exponential equation. Because this is really the motivation behind a logarithm. So let's just say I had the equation 2 to the power of x equals 8, and you wanted to solve for x. Well, what you might know is that 2 to the power of 1 would be 2, 2 squared is 4, and 2 cubed is 8. So this actually tells you the answer just kind of based on what you know from exponentials. This tells me that x equals 3 is the solution. And this is a great way to solve exponentials, and this is what we're going to rely on a lot of the times is our intuition. The problem is there's other times where we end up with something like 2 to the power of x equals 5. Now notice over here, none of these gave me the answer of 5. We got 2, 4, 8, the next one would be 16. So the question is, well, what is x? And this plagued mathematicians for quite some time until someone came along and said, well, let's just say there is a number that works for x. We don't really know what it is yet, but we're going to use something called a logarithm. And they define the log, is how I'll abbreviate a lot, but the logarithm is the inverse function of an exponent. Just like we have plus and minus, our inverses. We have multiplication, division, our inverses. We have square roots, and to the power of 2 squares, our inverses. The same is true for log and exponents. These are going to be inverses of each other. And so what they said is, well, x has to equal something. We're going to call it log. They keep the base the same, so that 2 is going to show up kind of smaller and it's going to be underneath there. So it's log base 2 to remind us that the base of the exponent was 2, and then we write of 5. So this was color-coded in this case. If I were to solve this, my answer would just be log base 2 of 5. And that's it. Just like we have, sometimes we'll say the square root of 2 is the answer, and we'll leave it at that. We would leave this as log base 2 of 5. Now, you'll notice up here that 5 is somewhere in between 4 and 8. So that means that it's probably 2 to the power of 2 point something that's in between 2 and 3. And you're exactly correct. I'm not so concerned with the decimal approximation of this at some point. We could say it's approximately 2.2 ... whatever it is. But I'm really more interested in just kind of defining a logarithm. So this brings us to the next step. Here is sort of the formal way to write this. If you're given some exponential expression, let's call it b. Actually, I think I'm going to color code this. So let's say it was b to the power of x equals y. Then to rewrite this as a logarithm, you would say whatever's in the exponent, in this case I have an x there, x equals, let's do log base b of y. And this is really a formula. This is something you should have written down in your notes. You should have this memorized. You should really know this inside and out. Get it tattooed if you have to, whatever you need to do to remember this. This is going to be really key throughout the entire lessons, the next couple of lessons that we do in this chapter. All right. So let's immediately apply this definition and evaluate some logs. So we are going to actually go ahead and evaluate some values. So let's say we're trying to figure out what log base 2 of 8 equals. So I'm not really sure what this is, log base 2 of 8, but we can think of this as an exponential. We could say that this is x equals log base 2 of 8. So therefore, if I convert this to an exponential equation, 2 to the power of x equals 8, now we're actually into the same situation I started with. And so you'd say, oh, well, log base 2 of 8 actually equals 3, and that would be your final answer. So let's stick with some maybe more straightforward problems. We're going to do log base 3 of 9 now. So the question we're really trying to ask is, if I set this up, we're trying to say 3 to something, I don't know what that something is, equals 9. And so this you might have to do a little bit of work, or you might just know, but 3 to the power of 1 is 3. 3 squared is 9, and oh, there's the answer. So we would say log base 3 of 9 equals 2, and that would be our final answer. And then the last one I want to do is log base 6 of 1. So in this case we're saying, well, what is this x value that makes this equation true? 6 to the power of x equals 1. Now this one might be a little bit trickier because 6 to the power of 1 is 6, 6 squared is 36, so we're going the wrong way. We're not getting to 1. However, you might remember, if you do 6 to the power of 0, really anything to the power of 0, you actually do get 1. So the answer in this case would be x equals 0. So that means log base 6 of 1 is going to be 0. And so this is how I like to think of logs. Log is sort of the missing exponent. Whenever you're doing a logarithm, it's like you're trying to find what that exponent is. Okay, now we've built up some intuition hopefully on logarithms. There's a couple of definitions I want to give you, and I probably should have done at least one of these beforehand. So we're going to kind of take a sidetrack from logs for a little bit. The first one I want to define is the natural number e. It's kind of like the number pi. So e is number, it's called Euler's number as well. It's spelled like this, Euler's, but it's pronounced Euler's number. And this is a number that, strangely enough, shows up a lot in nature, just like pi does. Pi is kind of another one of those weird numbers that goes on forever and ever and ever, but it's just kind of weird that it shows up with circles. E is this number. It's about 2.718, but we never really write 2.718, just like we never write 3.1, well, I sometimes we write 3.14, but usually we just write pi. Same thing is true with e. So we'll be using e quite a bit as a base. E gets used as a base in exponential and logarithmic problems. So what we're going to do now is define a couple of logarithms, some special ones. So sometimes you'll see just log show up, say log of, I don't know, 23, and you won't see the base here. So notice the base is kind of missing. If that's ever the case, this is assumed to be log base 10. And this is called the common logarithm because we use base 10 so much. mathematicians got tired of writing it over and over and over again. They decided to be more efficient. And they said, let's just assume if you see log without a base, that means base 10. The other one that shows up a lot is log base e, but they already used log without a base. So what they said was, let's make ln, which stands for logarithm or natural logarithm, but it's in reverse order. So if you ever see, say, natural logarithm of, I don't know, we'll just do 23 again. This means log base e of 23. This is called the natural logarithm. All right, so this video was mostly devoted to definitions and just kind of building your intuition with logarithms. In the next video, we're going to do a little bit more evaluating and some level 1 solving as well.